Panacea automating attack classification for anomaly-based network intrusion systems. I'm going to start with the introduction of intrusion detection systems. There's predominantly two types that are in place: signature-based intrusion detection systems and anomaly-based intrusion detection systems. The signature-based intrusion detection systems detect attacks for which a signature has previously been created. It's attack, analyze, respond. The advantages of a signature-based intrusion detection system is signatures are determined by previous packet analysis. Signatures are classified easily since they are quantified and qualified in advance. They can determine the cause of the alert due to previous analysis. Disadvantages: they don't respond to new zero-day attacks or complex attacks. So the information that they analyze has been captured previously. Basically, a trigger sets it off, and then it's classified based on that previous analysis. That's a signature. That's a screenshot of a common signature-based IDS. As you can see, I put it on here because it kind of indicates levels. You can see that just from the GUI that it's already got classification built into it, just in the way that it's been established. Okay, anomaly-based intrusion detection systems. Anomaly-based intrusion detection systems is a system for detecting computer intrusions and misuse by monitoring system activity and classifying it as either normal or anonymous, abnormal or normal. The disadvantages it can prevent complex attacks or new zero-day attacks. Works best on network baselines, and disadvantages are difficulty in defining rules, and the baseline must be fully tested. So these are behavior triggers. If you start off with a baseline of your network, common network activity, and you say, okay, this is good, this is normal traffic. You train your intrusion detection system, and then it triggers anything that's basically different than that. And just through its development, it really hasn't defined the classifications, because there's kind of more ways to attack. So it just really hasn't developed a classification system as strongly as signature-based. That's a screenshot of a common anomaly-based intrusion detection system, Poseidon. And as you can see, it just doesn't have as much info. This is just an illustration of kind of anomaly-based, just saying, hey, this happened. We don't know exactly what it was, but something different happened. So, and as you can see, you just have some graphs, and there's not a whole lot of indications of levels or severity of the intrusion. And signature-based intrusion detection systems are more traditional, because of the way that coding was developed in general for computer scientists. Signature-based it was more closely defined as compared to anomaly-based. In signature-based, if it's this, then do this. Anomaly is, okay, it's not this, and it's not, then we don't really exactly know how to respond. It's just indicating that that something abnormal has happened. Okay, so signature-based IDS and anomaly-based IDS. In implementation, it's actually best to have both, right? Because you want the classification and the quick response of a signature-based IDS, and you also want to have the zero-day attack prevention that you get from anomaly-based IDS. So you really want to deploy both these systems so you'll have kind of full knowledge of what's going on. However, it's hard to manage with a SIM or a SIMS. You want to achieve the best of both of these two worlds, and that's kind of where they got the title Panacea. It's a solution for all things. So recently, SIMs have become prevalent because people are paying more attention to network security. So they needed an easy way to manage network security logs. So these types of applications have recently been more prevalent due to the huge number of logs that we have. And it brought up an issue with these two IDSs. A SIM needs to have kind of precise information in order to classify and respond. SIMs can actually do automated things with their responses, but they need precise information. So anomaly-based IDSs created a problem for using SIMs. I'll just read these as well. The software products are used to simplify management and awareness. It can be used to perform tasks automatically, alert filtering, correlation. It can trigger automatic countermeasures, and they must classify information in order to be relevant. It's easy with signature-based, hard with anomaly-based IDSs. So that's the problem. Anomaly-based IDSs cannot associate alerts with attack classes. No automatic or semi-automatic approach is currently available. It must be classified to respond to it correctly. Manual analysis increases the workload on security teams, and the lack of classification makes it difficult to employ alert correlation techniques. Also makes it difficult to activate automatic countermeasures. So we need to figure out a way to classify these things. The proposed answer from the authors is to use machine learning techniques to automatically and systematically classify attacks detected by a payload-based anomaly-based system. They do this by extracting byte sequences from alert payload and compare those sequences to previously collected data with an algorithm to infer attack class by matching alert payload class. It requires a training phase. And in this case, only payload based attacks can be classified. Okay, so the author's architecture in creating this process is an alert information extractor. It receives alerts from the IDSs, processes their payloads, and extracts significant information, and it outputs that meta information about the alert. The other part is the attack classification engine. It automatically determines attack class, and it's trained by feeding it several alert metadata information to build a classification model. It can also be manually created by an operator or automatically by extracting additional info from the alert. Extract all the info and then classify it. Here's an overview. It's a very high level overview. As you can see, Poseidon, anomaly-based intrusion detection system on top. Snort is the signature-based intrusion detection system. This is a really simple slide. It just feeds that information into the alert information extractor. The AIE passes that it pulls pieces of that information out, passes it to the attack classification engine that then classifies those alerts. Then we can do our appropriate action based on those results. Okay, the alert information extractor. Its requirements are it should capture enough info from the original info to distinguish different classes. It should be efficient with respect to required memory space. So that's a problem with storage and efficiency. So the authors indicate the usage of high-order n-gram analysis. It kind of uses a sliding window to take smaller samples of the data. Shannon had a principle. We're given a sequence of letters. What's the likelihood of the next letter? It captures more data and consequently more precision. Storage is, however, storage is increased exponentially as order or features increase. And they also use or talk about the implementation of a Bloom filter. A Bloom filter saves space via compactness, inherited arrays, and probabilistic nature. You check to see if an element is not there as opposed to being there. you also can check the probability of existence before performing workload. So n-gram analysis. What is it? It's a contiguous sequence of n items. It's a probabilistic statistical model for predicting the next item in a sequence. You analyze the data and build statistics to provide information about its context. Example is with speech recognition. Statistically analyzed so that it can determine the correct context. It makes the information more accurate. For example, the probability of an n-gram 15 minutes from is greater than the probability of an n-gram 15 minuets from. So it basically adds accuracy. Okay, the advantages and disadvantages of n-grams. It allows us to capture data more efficiently, like I mentioned. Allows us to capture more data features and provides more accuracy. Higher order n-grams give us more info. However, as n-gram order increases, storage increases exponentially and becomes infeasible. It's too large to store in main memory, and if stored on the disk, becomes too slow and inefficient for storage and retrieval. An example would be 640 gigs needed if you were going to store an n-gram on the order of 5. So the authors chose to use a binary n-gram since they're more concerned with whether or not something occurred as opposed to a statistical characteristic of that data. And basically, it's just too much space. That's the reason they went to binary n-gram. And it leads to Bloom filters. So what is it? It's a kind of a complicated structure or concept. It's a method of representing a set of elements into a smaller space. So I'll read you the definition of it. It's a pair BH where B is a bitmap of L bits initially all set to 0, and H is a set of K independent hash functions, H1, blah, blah, blah. For each n-gram S in a set, and for each hash function HK, we compute HK mod L, and we use a resulting value as an index to set the bit in B corresponding to it. When checking for the presence of a certain element S, the element is considered to be stored in the Bloom filter if and only if HK B HK S mod L equals 1. A Bloom filter with a size of 10 kilobytes is sufficiently large enough to store the alert metadata resulting from 5-gram analysis. So it's a huge benefit on space and efficiency. Okay, I'll talk a little bit more about a Bloom filter. Like I said, it's a fast and efficient data structure used to check for set membership. It can tell you if an element is definitely not in a set or that it's probably in a set. However, it can't tell you if an object is definitely in a set. And you can't use a single hash of all the elements due to the size, potential collisions, which could result in a false positive. It says it's in the set even though it's not. Using just a hash can also result in a response due to collisions that it is definitely in a set when in reality it's not. This is the worst case scenario since you just missed something that could cause damage. Bloom filters use multiple hashes and set the resulting bits at various locations to decrease the chance of false positive, saying that it's in the set but in reality it's not. And it cannot result in a false negative, saying that it's in the set but in reality it is. So these two, a little small in this, but these two images are just indicating, they're just showing the way that Bloom filter hash is inserted. On the slide on the left, you can see that it basically takes a string, does 3 hashes, and puts the resulting bit in an array. It shows the first part where it's inserting one string, and second where it's inserting a second, and it's using different different areas in the bit array. The second one actually is an example of a false positive, illustrating the method of bloom filters could result. And yes, it's in my set. In reality, it's not. So you can see the collisions when it tries to insert that new string. Remember that bloom fields cannot tell you definitively that an element is in a set. It was still a little confusing to me. And then I ran across a couple of examples. This one was the clearest one. And it essentially shows you the whole process. So what we do is we have, in this bloom filter, we have three elements in the array, and we use a bitmap. I forgot to mention that. Bitmap is actually the best storage for a bloom filter. So as you can see, we take Fred, and this particular example uses 2 hashes. We take Fred and we hash it once, and we get one result 21, second 14, using a different hash. We place those bits in the bit array, and then we go on to the second one. So we add an element each time, and it results in this bit array. You can see the positionals based on the hashes. And then when we need to look up an element to make sure it's in there, then we just have to. So as you can see, like Amy is on the next is the test case. You can see that in 16 and 12 there is no 1, so we can say that Amy's not there. The second test case, we see that using the hash values, we see that Greg, we test to see if he's in there. If there's a 1 in 11 or the 22nd row, and we can see on the second one that there is a 1, indicating that he may be in that group. And that's a really clear way to indicate how it works. It's pretty simple in its implementation, but kind of hard to describe. Okay, so the attack classification engine, we're going on to it now. So it's got support for multiple classes, classification of high dimensional data, fast training phase, and then there's optional estimate of classification confidence. So authors use 2 non-incremental algorithms for experimentation. They're non-incremental because they don't need to rebuild the whole model whenever it changes. And the 2 methods they used are support vector machines and Ripper rule learner. Support vector machines are binary classifiers. They transform data into a higher dimension. Then it searches for optimal separation of the higher plane via vectors. It simply creates an overview to determine separation for classes. So you can see in the illustration, it takes the analysis that it performs and it plots it out. And as you can see, the slanting line there indicates the separation. Because the information falls in these different regions, they can clearly classify the differentiation. Ripper is kind of like an if-then algorithm. It's a fast rule induction algorithm. Conclusion contains a class prediction. Employs ordered rules and will break out if it encounters a match. Has a growing and pruning phase. Continues to add ifs one at a time until it matches, and heuristically removes and simplifies. The implementation of these. The implementation was written in Java. It's just an application that takes advantage of libraries provided by the Wiki platform, just to save time in coding. Wiki contains implementations of SVM and Ripper, so it was appropriate. And Wiki provides a framework. Payload info from extraction is stored and retrieved from a database. So it just made a good library to use. That's why they chose Java. The benchmarks. The benchmarks for the classification process were very difficult since there's not a lot of previous data sets to compare. There just hasn't been a lot of research. This is a new research field. So authors created 3 data sets: a DSA, DSB, and a DSC. The DSA is an automatic mode. The DSB is an ad hoc or manual mode, and the DSC is a mode for known attacks. The benchmarks results. Classification accuracy is always higher than 75%. The SVM, or the vector machines, are better when there's less number of alerts and more diverse alerts. Ripper works best when there's a high number of alerts used in training. And then, as I mentioned previously, SVM can be used, vector analysis can be used to optionally assign confidence of the classifications. Conclusion. So, Panacea extracts info from alerts and predictions and predicts the attack class. It can be used with signature-based and anomaly-based systems. Integrates signature-based and anomaly-based systems. Panacea is accurate and can be tuned to provide higher levels of class confidence. So this article is 6 years old, and since writing it, many software development companies have started using the same methodology in their next generation security systems. And I mentioned McAfee and Sophos. There's a ton of them because that's a new thing that's coming out. Also, there's been some research on mega intrusion detection systems that use the same approaches and apply many more approaches in attempts to protect all layers of the environment. Software vendors are starting to create IDS suites that employ different methodologies to prevent intrusion packages as one implementation that includes built-in management tools. So they're starting basically to do the same thing that these guys proposed and developing it further. They're coming up with whole suites that are basically different types of intrusion systems that that address different shortcomings in network awareness. And they're also creating management tools, which is actually just as important to let people know what's going on clearly in this onslaught of information that we're collecting nowadays. And that's it.
Right. Thank you very much.